pleasure to see so many old friends here. Thank you for coming. The celebration of the 50th anniversary of the Stat Lab is, for me, and I expect for many of you, a celebration of Jersey Neyman. And of course, that immediately raises the question, what would Neyman think of celebrating him by having 2 Fisher lectures? I think I know. I think Neyman would be amused and pleased. I can see the grin creeping across his face now as he thinks about it. What Fisher would think of that idea, though, I'm not so sure. The title of my talk is Likelihood and Sufficiency. Both these concepts were introduced by Fisher, and they're both fundamental in statistical inference. Like any good Baptist sermon, my talk has a text. A text is a short passage taken from the sacred writings that's the basis for the talk. Actually, I have 2 texts. One is on likelihood, the second is on sufficiency. Here's the likelihood text. The method of maximum likelihood is much used and widely appreciated in the statistical literature without, I fancy, so much appreciation of the significance of the system of likelihood values at other possible values of the parameter. In the theory of estimation, it has appeared that the whole of the information supplied by a sample is comprised in the likelihood as a function known for all possible values of the parameter. Now, Fisher is saying 2 things here. First, you should look at the whole likelihood function, not just at the value of the parameter that maximizes it. The whole likelihood function, he says, you should look at. Secondly, he says, for estimation, that's all you need to look at. So this is the text, then, for the likelihood part of the talk. Now, the Bayesian interpretation of the likelihood is all you need to look at says that if you know the likelihood and the prior distribution, you can calculate the posterior distribution. That the likelihood is all you need from the sample in order to calculate the posterior distribution. That's a Bayesian interpretation of Fisher's statement that the likelihood is sufficient. But more than that, not only is the likelihood all you need to calculate the posterior density, to a first approximation, the likelihood is the posterior density. That's the Bayesian gloss on Fisher's statement that the likelihood is all you need to look at. That the likelihood function to a first approximation is the posterior density. Savage said essentially that. He called it the principle of stable estimation. Let's look at some examples. The likelihood function is the posterior density. Example 1, you take a sample of size n from a Bernoulli distribution with unknown p. Here's the likelihood function. P to the s, 1 minus p to the n minus s, where p is the number of successes, and n minus, where s is the number of successes, n minus s is the number of failures. Likelihood principle says that's the posterior distribution of p. What is it? Well, it's a beta distribution with parameters s plus 1 and n minus s plus 1. So what does that tell you about the parameter? It says it has mean s plus 1 over n plus 2, and standard deviation, the square root of the mean times 1 minus the mean divided by n plus 3. If you compare that with the classical statements that are used to construct confidence intervals, the sample mean is the population mean plus or minus p, 1 minus p over root n. But notice that the Bayesian estimate of p is s plus 1 over n plus 2. The classical estimate of p is s over n. This is absolutely typical. If you take seriously this statement that the likelihood function is the posterior density, and you see what it says in particular cases, what it says is formally almost identical with what classical inference methods will give you formally. Of course, the interpretation of the parameters is different, and there will often be a slight difference, just as here it's s over n compared to s plus 1 over n plus 2, but they're virtually identical. Let's look at a second example. The likelihood function is the posterior density. Example 2, x is a sample of size n from a Poisson distribution with parameter lambda. You write out the likelihood function. L of lambda, the likelihood is e to the minus n lambda, lambda to the s. We all recognize that as a gamma distribution. The parameters s plus 1 and n. So this statement tells us that the posterior distribution of lambda is gamma with parameters s plus 1 and n. So the mean is s plus 1 over n. Standard deviation is root the mean over n. Again, compare that with the classical statement about the sample average. The sample average has mean, the population average, and standard deviation, the population average over root n. Lambda bar is the sample average. Again, close formal similarity. The only difference is you have an s plus 1 here for lambda caret, and you have an s for lambda bar. One third example. This time, we're sampling from a normal distribution with unknown mean and unknown standard deviation. The likelihood principle says that the posterior distribution of the two parameters, mu and h, is given by the likelihood function, and there it is. I won't read it. Now, we have now a joint distribution of two variables. To find the marginal distribution, you have to integrate them out, integrate the other variables out. If you integrate out mu, you get h, and that's a gamma distribution. I won't talk about that. But if you integrate out h, you get mu. And mu turns out to have a t distribution. In fact, the exact statement is square root of n times mu minus x bar over s naught is t with n plus 1 degrees of freedom, where s naught squared is summation xi minus x bar squared divided by n plus 1. Compare that with the classical statement. Square root of n x bar minus mu over s is t n minus 1, where s squared is summation xi minus x bar squared divided by n minus 1. Again, the formal conclusions from this principle are virtually identical with the classical conclusions formally, but the interpretation is different. Here, we have an n plus 1 replaced by n minus 1. It's the only difference. Notice this. All three of those distributions, the beta distribution for a Bernoulli p, the gamma distribution for a Poisson lambda, the t distribution for a normal mean, are all nearly normal for large samples. that is, large parameters. Well, that's not surprising. A general theorem proved by Lecomte and also by Walker and de Groot under various hypotheses say that posterior distributions from large IID samples are nearly normal. That's what we're talking about, posterior distributions. So it's not surprising that those three turn out to be all nearly normal. But notice this, there's something else about those three densities. They're all products of a large number of smooth functions. Consider the beta distribution. It's a function p to an s, a large power, multiply p by itself a large number of times a function 1 minus p, multiplied by itself a large number of times. Product of a large number of smooth functions. The gamma distribution. With n large, it's a product of a large number of functions. H, just multiplied by itself n over 2 times, and then times a single function, e to the minus kh. The t distribution. The distribution of it becomes clearest if you look at the square root of n times t with n degrees of freedom. It has the density 1 plus t squared to the minus n plus 1 over 2. It's a single function raised to a large power. It's not surprising that these densities are products of a large number of functions because they came from a sample of large size, and the way you calculate a likelihood function is every time you get a new observation, you multiply the previous likelihood by the likelihood from that observation. So all likelihoods from a sample of n are going to be products of a large number of functions, one for each observation. And it's a general fact that if you multiply together a large number of functions under quite general hypotheses, the product is going to be nearly normal. And when you say that to people, so there's that statement. If you multiply together 50 functions, you will get about e to the minus z squared over 2. Now, of course, that's true because I haven't told you what that means. And what that means is often suitably scaled, nearly equal to, for moderate values of z. Say z less than or equal to 0.5. A common reaction when people hear that is to say, really? Remarkable. Amazing. Product, not sum. And then you explain that you take logs of this, and you find that what it says when you take logs is that the sum of a large number of functions is about minus z squared over 2 near its maximum. In other words, large sums are nearly quadratic near their maximum. So that's what the same statement says when you take logs. Then, of course, people say obvious, trivial. Everybody knows that. So it's a bit of both, I think. It's a bit of amazing and a bit of obvious. But anyway, it's important. Here's what von Mises said about that in 1946. Von Mises knew this very well. He says, in this section we shall derive 2 theorems concerning the product of an infinite number of functions of one real variable. Such functions play a decisive role in probability. They were discovered by Laplace, who devoted a considerable part of his analytic theory of probabilities to this problem. And a little later he says, this is the first result. The product of n functions, all of which have a regular maximum equal to 1 at x equals 0, tends toward the Gauss function, e to the minus z squared over 2, in the sense of equation 7, which I haven't written out. It's sort of like those 3 wiggles, under the conditions A and B. So von Mises knew that Laplace knew that if you multiply together a large number of functions the product will be nearly normal. Actually, it's not at all necessary that they should have their maximum at the same point, as he's saying here. For instance, here's an example. Here's the unit interval, and here are several functions, all linear. Multiply together all those functions and normalize it. What do you get? I'm not sure how well you'll be able to see this. Let's see. Yes, it's sort of visible. I believe that the bottom curve is for 25 functions, and this one is for 50, and this one is for 100, and there's one in there that's for 200, but it's so close to the normal curve that's on top that you just can't distinguish the two. So it's just a fact under rather general circumstances. If you multiply together a large number of functions, you get nearly a normal curve. And that helps you to predict that certain distributions will be nearly normal. For instance, there's an F density with m and n degrees of freedom. And you see it's a product of x a large number of times and 1 over x plus r a large number of times. So you conclude that an F density is nearly normal for large m. In particular, for likelihoods, it's not at all necessary that they should come from IID observations. Anytime you multiply together a large number of likelihoods, whether they're from the same experiment or not, you're going to get a nearly normal likelihood function. For instance, suppose you're interested in a p, a probability between 0 and 1, but you can't take samples that have the value 1 with probability p and 0 with probability 1 minus p. But what you can do is to observe items connected in series and see whether the item works or not. Of course, it'll work with probability p square and fail with probability 1 minus p square. And you can examine items connected in parallel so that the item, and observe whether the item fails or not. The item will fail only if both components fail. And if you if you do a large number of experiments of this kind, there will be the likelihood function. You just multiply p squared every time you do a series and get a success and so on. And you get a product of a large number of functions like that. And it'll be nearly normal. I've plotted this for A, B, C, and D somewhere between 25 and 50. And it's just indistinguishable from a normal curve. So, Fisher told us that all you need to look at is the likelihood function. Now we see that likelihood functions are nearly normal. All you need to know a normal curve are two numbers, the mean and the standard deviation. So what are these two numbers then that will tell us all we need to know? Answer: the mean of this normal distribution is approximate. You can approximate it by the maximum likelihood estimate. And the reciprocal of the variance of that normal distribution is given by this formula. It was introduced by Fisher and called the Fisher information. So not only was Fisher right in telling us that the likelihood function is all you need to know, the two numbers that he introduced are the two numbers that you need in order to approximate the likelihood function. So Fisher was right on top of this problem. Now let's go to the second part of my talk and the second text. Here then is what Fisher in 1922 said about sufficiency. The statistic chosen should summarize the whole of the relevant information supplied by the sample. In mathematical language, we may interpret this statement by saying that if theta be the parameter to be estimated, theta 1 a statistic which contains the whole of the information as to the value of theta, which the sample supplies, and theta 2 any other statistic, then the surface of distribution of pairs of values of theta 1 and theta 2 for a given value of theta is such that for a given value of theta 1, the distribution of theta 2 does not involve theta. In other words, when theta 1 is known, knowledge of the value of theta 2 throws no further light upon the value of theta. I want to call your attention to two things about this statement. First, notice the notation. He uses the letter theta for both parameters and statistics. That suggests that in Fisher's mind there was not the sharp distinction between parameters and statistics which many modern statisticians tend to make. He thought of them as apparently rather similar objects. I think he was right in that. The other thing I want to call your attention to is this in other words. So he says something up here, and he says in other words, and then he says something down here. Let's look at those statements. Fisher has three numbers, quantities that he's interested in. A parameter theta, a statistic theta 1 that he wants to say is sufficient, and another statistic theta 2. Now, his statement before the other words said that given theta, given theta, the distribution of theta 2 is independent of theta 1. That is to say, if you're going from west to east, and you're at theta 1, and you want to say something about theta 2, you don't have to remember where you came from. Then, in other words, given theta 1, theta 2 throws no further light on theta. That says, if you're going from east to west, and you're at theta 1, you can forget about theta 2 in trying to say something about theta. Well, they look a little different. One talks about going from east to west. In other words, from west to east. You see, it's not clear that those two things are the same. In fact, they look different. Now, I'm going to call the east-west, I'm going to call the west-east direction Fisher. Even though, as you saw, he actually said something about both directions, but I'm going to call this direction Fisher because that is the definition that is usually taken for sufficiency. A statistic is sufficient if the conditional distribution of any other statistic given it. What? Oh, thank you. Yeah. Theta 1 is sufficient. I think it's all right, yes. If given theta 1, the distribution of theta 2 does not depend on theta. That's one of the things that Fisher said in 1922. In 1942, Kolmogorov defined sufficiency. Kolmogorov's definition went this way. He said theta 1 is sufficient if for every prior distribution, the posterior distribution, given the whole thing, depends only on theta 1. Kolmogorov said, if theta 1 is sufficient, if that's all you need to calculate the posterior distribution given theta 1 and theta 2. So that's going in this direction. Kolmogorov said, however, that this was Fisher's definition in another form. Well, yes, it was in the form that you get by reversing that arrow. And I'm going to call that Bayes sufficiency because it refers to calculating posterior distributions. Now, so are they the same? Well, Fisher sufficiency does imply Bayes sufficiency. And the proof sort of goes like this. If you take any prior distribution on theta, then Fisher sufficiency says that this triple, theta, theta 1, theta 2, is a Markov triple. And it's a standard probability theorem that a Markov triple is Markov in reverse. Therefore, you can get that theta 2, theta, theta 1 is Markov, and that's really Bayes sufficiency. So Fisher's definition is, if anything, stronger than the Bayes definition. It implies Bayes. You can try to reverse this argument, and it almost reverses, but you have to exclude a theta set of measure 0, depending on the lambda that you take. And so you don't quite get Fisher's definition. Well, that doesn't mean that they aren't the same. It just means that I don't know how to prove that they are the same, or I haven't proved that they are the same. Some other authors that I like very much have asserted that they are the same. However, if you look not where they make the statement, but a few pages back in the book, it turns out that they said, from now on we are assuming that all distributions are mutually absolutely continuous. And under that hypothesis, yes, they really are the same. And the one proof of that, well, we already went in one direction. Fisher implies Bayes. Bayes always implies pairwise Bayes. And pairwise Bayes always implies pairwise Fisher. And under this hypothesis, it's a fact that pairwise Fisher sufficiency implies Fisher sufficiency. So it's not that these fellows were wrong, it's just that you had to look 3 pages from where they stated the theorem to see that it really was a correct theorem. So the question remains, are they the same? And the answer is, of course, no. I wouldn't be going on like this if they were all the same. And so I'm now going to describe for you an example of a situation of triple, theta, theta 1, theta 2, where theta 1 is Bayes sufficient, but not Fisher sufficient. It's most naturally described as a test of a hypothesis H0 against an alternative H1 that has the property that there's a perfect Bayes test, but no perfect classical test. By that I mean that if you put a prior distribution on all the parameters in H0 and all the parameters in H1, then you can find a test that decides perfectly with probability 1 whether the true parameters in H0 or whether the true parameters in H0. However, no matter what test you take, you can always find some parameter value for which it will be wrong, in fact, with probability 1. So that's the example that I'm now going to describe. You observe a sequence of zeros and ones, a whole infinite sequence you observe. And you know that this came from some 0-1 process, which is either converging to 0 with probability 1, or is converging to 1, converging to 0 in probability, or is converging to 1 in probability. You're given that. And you want to test the hypothesis that you're dealing with that this x came from a distribution that's converging to 0 in probability, against the alternative that this x came from a distribution that's converging to 1 in probability. And the problem is, how well can you test? Oh, I'll call this a small distribution and this a large distribution. Intuitively, you can think of it in this way. You see an infinite sequence of zeros and ones. And you're trying to decide, does that infinite sequence have mostly zeros or does it have mostly ones? Now, of course, that's not quite a precise way of formulating it, but we often think about problems in not precise but intuitively helpful ways. So that's what you're trying to test. So I have two things that I want to say to you. First, that a Bayesian can test perfectly whether the sequence you're looking at has mostly zeros or mostly ones in this sense, and a classical statistician cannot. As for any rejection region, there is an X against which that rejection region is wrong with probability 1. So I'm going to answer two questions. How does a Bayesian test perfectly, and what goes wrong with any classical test? In the Bayesian approach, if you put a prior distribution on the parameters in H0 and a prior distribution on the parameters in H0, the average of all the parameters in H0 is just a distribution itself, and so the average of all the distributions in H1 is a distribution itself. So you reduce testing H0 versus H1 to a simple hypothesis, namely testing the average distribution under H0 against the average distribution under H1. So in the Bayes formulation of this problem, you just have two given distributions. And it turns out that the average of all distributions in H0 is itself in H0. Any average of distributions in H1 is itself in H1. So you just have the simple question, am I looking at a sequence that is converging to 0 in probability according to a known distribution, or am I looking at a sequence that is converging to 1 in probability according to a known distribution? If a sequence converges in probability to 0 according to a known distribution, you can select a subsequence that converges with probability 1. And you do that, and you get a subsequence of the x's that's converging with probability 1, either to 1 or 0. Well, anybody knows how to look at a sequence of zeros and ones and tell whether it's converging to 1 or 0. If it's converging to 1, it'll be 1 from some finite point on. If it's converging to 0, it'll be 0 from some finite point on. So the Bayesian test then is simple. You just look at the average distributions and then look at the subsequence that converges with probability 1. Now let's ask the question, why does every rejection region fail for some x? Let's think of the problem then, looking at a sequence of zeros and ones and trying to decide, does it have mostly zeros or does it have mostly ones? I'm going to suggest a plausible criterion that you might use and then show you why that doesn't work. And the general argument is rather like that. Here's the plausible criterion that I'm going to propose. You look at this sequence and you calculate the frequency of ones in the first n places. That frequency will oscillate. If it's bigger than a half infinitely often, then I'm going to say that sequence has mostly ones. But if it's not bigger than a half infinitely often, I'm going to say that sequence has mostly zeros. So that's my test R. That's my test region. It turns out that says that too many sequences are large. So it's my job then to produce a distribution of x that is actually converging to 0 in probability, but such that infinitely often in that sequence, the frequency of ones is going to be bigger than a half, even though it's converging to 0 in probability. Well, so here's what I'm going to do. I'm going to produce a sequence such that the probability that the nth coordinate is 1 goes to 0 as n becomes infinite, but the frequency of ones is bigger than a half infinitely often. The space is going to be the unit interval. All this is going to take place on the unit interval, and I'm going to graph the indicator function of the regions. I'm going to graph xn, actually. Here's x1. It's always 1. So the idea is, x1 is always 1. x2 and x3 are identical. They're both 1 on the interval 0 to a half, and 0 on the interval a half to 1. x4 up to x7 are identical. They're all 1 on the interval 1/2 to 1, and 0 there. Then I come back and start sweeping the interval again. The next 8 x's are all 1 on the interval 0 to 1/3. The next 16 x's are 1 on the interval 1/3 to 2/3. The next 32 x's are 1 on the interval 2/3 to 1, and so on. You see how I'm constructing these x's. So the idea is you pick a point at random in the unit interval, and then I tell you which of these, I tell you the values of the x's. In other words, I tell you which of these intervals it's in. Notice that if you pick a point at random, the chance that it's going to be in the interval corresponding to xn is small, because xn is 1 on a small interval if n is large. So the xn's are going to 0 in probability. But if you pick a point in the interval, no matter how many x's you've looked at, these intervals are going to sweep across, and eventually that you will run into an interval that contains x, that contains the point you picked. When you reach that interval, you repeat it more times than you had x's up to that point to force the frequency of 1s above a half. Now, it happens only very occasionally, but it happens infinitely often. Now, this shows you just that this special criterion for deciding when a sequence has mostly 1s fails. The general criteria, the general argument for showing that every criterion fails is not really very different from that, but I'm not going to describe it. Now, how do we relate that to sufficient statistics? Theta is the distribution of x. That's the parameter of interest. Theta 1 is the variable x itself. It's this infinite sequence of 0s and 1s that we see. Theta 2 tells us something about theta. It tells us whether the distribution theta is converging to, has xn converging to 0 in probability, or has xn converging to 1 in probability. So we have a parameter theta, an observation x, and theta 1, and another observation theta 2, both of which we could get from theta. Now, theta 1 is Bayes, but not Fisher sufficient for theta 2. Why is theta 1 Bayes? Because given a distribution over theta, we just saw that when you observe x, you can calculate theta 2. In a Bayes sense, if you observe x, you can test perfectly whether x is small or large. That is, you can calculate theta 2. But it's certainly not Fisher sufficient for theta 2, because if you wanted to test the hypothesis in the Fisher sense, in the classical sense, that theta is small against the alternative that it's large, you could test it perfectly if you knew theta 2. That's exactly what theta 2 tells you. But you can't test it perfectly using theta 1, because we just saw that if you have any test based just on x, there's always some theta for which x is wrong. This interpretation of this example is due to me and Ramamurthy in the Annals of Statistics, 1982. So, this raises the question, What would Fisher think of this example, showing that what he said after the in other words was different from what he said before the in other words? I suspect that he would have dismissed it as being irrelevant to statistical practice, and perhaps he would have been right. But I think Naaman would have liked the example. Thank you very much.